Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New St. Augustine.
At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the U.S. Independence Day, I made the first experimental measurement of the world's fastest computation ever recorded across an ensemble of commodity off-the-shelf processors. That experimental discovery represents a new way of looking at the computer. In the new way, the new computer would become a web of 1 million interconnected processors, and the new computer will have as many email pathways by which its ensemble of processors communicate. To be the first is a greater achievement than to be number one or to be the fastest. There's only one first, but there will be many fastest. I was the first to discover that parallel processing across an ensemble of the slowest processors is faster than sequentially processing only on the fastest processor or only on the fastest supercomputer. Prior to my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, I was ridiculed, mocked, and rejected by the vector processing supercomputer research community. After my experimental discovery of the 4th of July of 1989, the last team of vector processing supercomputer researchers that dismissed me from their group realized that they've made a mistake. Their mistake entered into the history books. A year later, a member of the supercomputer research team that dismissed me from their research group told the rest that his daughter wrote a school report titled, quote, "The Contributions of Philip Emeagwali to the Development of the Computer," unquote. After the 4th of July of 1989, it made the news headlines that I experimentally discovered how and why the parallel processing technology makes computers faster and makes supercomputers fastest. My experimental discovery of the parallel processing supercomputer opened the door to the field of the parallel solution of the numerical approximations of the partial differential equations of modern calculus that now enables extreme-scale computational mathematicians to massively parallel compute many algebraic problems and to compute them at once. My experimental discovery of the parallel processing supercomputer opened the door to the field of parallel computational fluid dynamics that now enables extreme-scale computational physicists to massively parallel compute many computer models and to compute them at once. My experimental discovery of the parallel processing supercomputer opened the door to the field of large-scale numerical algebra that now enables algebraists to solve millions of sets of systems of linear equations and to solve them at once. The modern supercomputer opened the door to the field of experimental mathematics and to using the fastest supercomputer to confirm analytical solutions and to using the fastest supercomputer to gain insight and intuition into a mathematical problem and to using the fastest supercomputer to test and falsify a mathematical conjecture. The modern supercomputer that is powered by massively parallel processing technology is an instrument of physics that extreme-scale computational physicists use to solve the most computation-intensive arithmetical problems. The computation-intensive problems of supercomputing arose from extreme-scale algebra that in turn arose from the most abstract partial differential equations of modern calculus. Parallel computing can best be explained to a 12-year-old as, quote, doing many things at once, unquote. I was in the news back in 1989 because I experimentally discovered how to do 64 binary thousand things and how to do them at once. My experimental discovery of how to massively parallel process and how to do so across 64 binary thousand processors opened the door that enables the world's fastest supercomputer to parallel process 10 binary million things and to parallel process them at once. For me, Philip Emeagwali, my quest for the experimental discovery of the parallel processing supercomputer began on June 20, 1974. My quest for the fastest parallel processing supercomputer began with one of the world's fastest sequential processing supercomputer that was in June 1974 inside the computer center that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. My quest was for the new knowledge or for the experimental discovery of how to compound an ensemble of processors or computers. My quest was for how to compound 65,536 or 2 raised to power 16 processors and compound as many computers. My quest was for how to compound processors or computers and how to compound them repeatedly and how to continue compounding processors to form a seamless, cohesive supercomputer. My quest was for how to continue compounding processors and for how to do so across the surface of a globe that I visualized as embedded into a 16-dimensional universe. My quest was for how to continue compounding processors and for how to continue until I had a global network of 64 binary thousand processors. That's how I, Philip Emeagwali, experimentally discovered my small internet that is a global network of processors. On June 20, 1974, and at age 19, I was like a mouse that was inside the computer center that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. For the next decade and a half, I grew to the lion that was protecting the world's fastest supercomputer. I grew to invent a new supercomputer that is called the Philip Emeagwali computer, that is a global network of processors. I grew to invent a new internet that is called the Philip Emeagwali internet. I was invincible in 1974, but I am now visible everywhere on the internet. Looking back, the Supercomputer Center was a lonely place to be a young black computer wizard. The small internet that I experimentally discovered was my prototype of a planetary-sized internet. That small-scaled internet was powered by 64 binary 1000 commodity processors. The experimental discovery that I made across that small-scaled internet made the news headlines in 1989, and it inspired the development of the modern parallel processing supercomputer that is powered by up to 10,649,600 commodity processors. My theoretical discovery of massively parallel processing was ignored for the decade that preceded 1989. I gave a massively parallel processing supercomputer lecture in November 1982. I gave the lecture in a conference auditorium that was a short walk from the White House, Washington, D.C. The abstract of my supercomputer lecture described my theoretical discovery of the massively parallel processing supercomputer. Only one computational physicist attended that supercomputer lecture. Those research physicists that did not attend my lecture of November 1982 joked that parallel processing is a beautiful theory that lacked experimental confirmation. My theoretical discovery of the massively parallel processing supercomputer was only accepted in 1989. It was accepted after I had experimentally reconfirmed massively parallel processing and reconfirmed it across a new internet that is a global network of 65,536 commodity processors. After a decade of directed effort, my theoretical discovery of the massively parallel processing supercomputer was confirmed experimentally on the 4th of July of 1989 and confirmed by me, Philip Emeagwali. To experimentally discover the massively parallel processing supercomputer, I had to combine physics insight that enabled me to invent partial differential equations of a new calculus that I discretized into large system of equations of a new algebra. I discovered how to solve that large-scale system of equations and how to solve it across a small internet. I visualized that small internet as my global network of 64 binary 1000 processors, or as a global network of as many computers.
insightful and brilliant lecture.